Hello and welcome to the web series, ZeroPM Pieces. In the ZeroPM Pieces, the researchers in the project will tell you about one piece of the ZeroPM puzzle that they're working on. So without further ado, here comes a ZeroPM piece.
All right, so welcome to ZeroPM Pieces number 18. My name is Lucas. I work at the DVGW Water Technology Center in Karlsruhe in Germany, and today we're talking about using ion exchange resins to clean PFAS contaminated water. So here's just a very brief reminder of the substances we're talking about. We have PFAS that are toxic and bioaccumulative. We know that some of them are mobile in the environment. All of them are basically persistent or degrade to persistent degradation products, and thus they enrich in different environmental compartments like animals, humans, plants, and water. And to reduce the release to the environment and to treat contaminated compartments, we need sufficient treatment methods. The challenges in PFAS removal are, of course, their biochemical stability, but also their wide range of physical chemical properties. Just to name an example, the difference between a short chain perfluoroalkyl acid like TFA compared to a long chain perfluoroalkyl acid like PFOA. And particularly the small mobile compounds like short chain perfluoroalkyl acids can be a big challenge here. So what treatment technologies do we have available? I took this framework here from a review by Ross et al. 2018. We can categorize the different methods for PFAS treatment in adsorption, like activated carbon ion exchange or polymeric adsorbents. Flocculation technologies or liquid-liquid separation, like reverse osmosis and nanofiltration. There are also destructive technologies like incineration and photolysis. What you see here is that all of these technologies are at a different stage of maturity and have been rated with a different practicality for a practical application. And when we look at the top right corner here, we see that ion exchange processes have been found to be very feasible for PFAS removal and are also at a quite mature stage already. So we have quite promising technologies here at hand. So how does it work? We have a resin with positively charged functional groups that can bind negatively charged ions. And we see this here on the left side, the resin part, and these counter ions on the resin can be exchanged by also negatively charged contaminant ions. And we can express this with a chemical equation. Important to note here is that it's no one-way adsorption, such as activated carbon is, but it is an actual exchange that is strictly stoichiometric in regards of charge equivalence, and it is also reversible. That becomes important when we talk about resin reuse and regeneration later on. This is just to remind you that the most common PFAS, the perfluoroalkyl acids, or most common PFAS in water, usually have a negative charge, so they can take part in anion exchange processes. And there are studies that indeed have shown that there are stoichiometric releases of, for example, chloride to water when these compounds attach to resins. The hydrophobic part can also be made use of by modifying the functional groups of resins in a way that they become more hydrophobic and thus are more selective towards PFAS sorption. I will show you some examples in a minute. So anion exchangers, or I should say organic polymeric anion exchangers, basically may look like this. We have tiny whitish, yellowish beads. When we zoom in into one of them, it may look like this with a polymer matrix, for example, polystyrene. If it's polystyrene, it's usually cross-linked with divinylbenzene. We have attached to that functional amine groups with a positive charge and the negatively charged counter ions define the form in which the resin is in. So we have, for example, the chloride form or also the sulfate form. To visualize it a bit more, we have our matrix, we have our charged functional groups, we have our counterions, we have our water phase containing our contaminants, and there are also some co-ions inside because of the principle of charge neutrality. When the contaminant ions have a decent affinity towards our charged functional groups of the resin, they can attach to the resin, and thereby a counterion is released into the water phase. So this leads to less contaminants in the water and a little bit more chloride, for example, in the water phase. Selectivity and efficiency of anion exchange processes largely depend on factors such as resin type, polymer matrix, the polystyrene versus polyacryl, functional group, tertiary versus quaternary amines, and also the attached alkyl moieties. The pore structure is more influential on the kinetics and less on the overall capacity of resins, but there are also studies that show that the ionic form or the counterion can influence PFAS sorption to resins. The concentration of contaminants can be a factor. When we have very large concentrations of PFAS, the efficiency is usually or maybe better than when the concentration is very low already. And there may be sorption competition that can influence selectivity and efficiency with different parts of DOC or other inorganic ions. And now I will show you some examples. They are all from our own research within ZeroPM, but there is also a lot of literature out there that basically shows the same principles. I will demonstrate here with how different resin characteristics can influence the PFAS sorption. So in this example, we did some batch experiments. You see the conditions here on the left. We shook the reactors until equilibrium with tested different resins with different characteristics and compared the absorption of perfluorocarboxylic acids and sulfonic acids. You see them ordered by chain length here at the bottom. The more green you see, the better the adsorption was. So we start with a macroporous acryl-based type 1 resin, and we see that basically for all compounds, the adsorption was less than 10%. If we change the acrylic polymer to a styrenic polymer, we see that the adsorption is much better. There are studies where this difference has been less prominent, but in the drinking water we did our experiments in, we had always a very significant difference between acrylic and styrenic type resins. We also see a chain length dependency, so the more hydrophilic short chain compounds have less sorption, and the more hydrophobic long chain compounds adsorb much better to the resins. This is because there is more opportunity to undergo hydrophobic interactions, for example, with the alkyl moieties of a functional group. And so we can also elongate the alkyl moieties at the functional groups. For example, here by changing the methyl groups to butyl groups, and we see that the adsorption increases. All these three types or three resins here are so-called strong basic anion exchange resins. That means that they are always, or their functional group always has a positive charge independent from the pH. This is not the case when we use weak basic anion exchange resins with tertiary, secondary, or primary amines. Here, when we increase the pH value, then we can deprotonate the functional groups and bring them in the so-called free base form. So they work better when the pH is lower. But this deprotonation can have some advantages I will get to in a minute. Because in general, we see that the performance of the weak basic resins is less good than the strong basic resins. And the same principles apply here. We see the acrylic resin is worse than the styrenic one. And if we take away here from the tetraamine to the primary amine, if we take away the methyl groups, the absorption is also weaker. We see the same principles when we compare breakthrough curves of a laboratory scale column test. Here, the weak basic resin we see at the top and the strong basic resin at the bottom. We also see the chain length dependency here, earlier breakthroughs for the smaller chain lengths. And we see that the breakthrough, the time until breakthrough is much later here when we compare TFA, for example, for the strong basic resin compared to the weak basic resin. So why would we still want to use weak basic resins? And the answer to that is regeneration. So I told you that this reaction is also reversible, and we can achieve this by increasing the chloride at this site, for example, and then increase the chemical potential and push the equilibrium to this side so that the attached PFAS is released again. Sometimes the hydrophobic interaction contribution is that high that we also have to weaken hydrophobic interactions by using an organic solvent, and we cannot use a regeneration in only water. It is a bit easier when we use the weak basic resins because we can just increase the pH and then we can deprotonate the functional groups, and desorption is facilitated. Side note, this regeneration process basically changes the anion exchange process from a pure adsorption process to an actual liquid-liquid separation process, comparable to reverse osmosis, but with much better liquid-liquid separation factors. It also makes the process more sustainable because we can reuse the resins. We can use it for more cycles, but it also generates highly concentrated waste streams. And if we don't want to release the PFAS from there into the environment again, then we need to pair it with appropriate destruction technologies. And even if we use weak basic resins for long chain PFAS, the hydrophobic interactions may still be too strong to work with a pure aqueous solvent or water, and we need to use an organic solvent. So with only water, it's only practical for short chain compounds. And using an organic solvent is not the most sustainable solution that you can think of. So there are different ways, maybe different ways to approach it. I will show you how we do it in ZeroPM. This is our vision of a sustainable PFAS treatment process for drinking water in this case, and maybe also for some other applications. We want to pair the anion exchange resin with another adsorption material in front of the actual anion exchanger, in this case activated carbon. And this activated carbon will filter will absorb the long chain compounds and attain it for a long time, so that the long chain compounds that are not really they don't desorb well from the anion exchange resin, do not reach the anion exchanger for a very long time, and the short chain compounds with early breakthroughs reach the anion exchanger, but they can be regenerated more easily. And when we use a weak basic anion exchanger, we can use an aqueous regeneration by just increasing the pH and do this regeneration regularly. So we can use the resin and the activated carbon for quite a long time. And then we need to pair the PFAS containing regenerate with a destructive technology. We are also working on that. But it's not part of this presentation. So I will show you some intermediate results of a pilot plant in which we paired activated carbon versus anion exchange, to make you excited, to tickle you a bit and make you more excited for further results in the course of the project. So we have groundwater contaminated with PFAS, and then we have activated carbon treatment and then an anion exchanger afterwards. And we see that in gray, the concentrations of PFAS increase in the effluent of the anion of the activated carbon filter within the course of 6 months of operation for now. And in blue, breakthroughs in the effluent of the anion exchange resin. And we see that when we regenerate on a regular basis, we can bring this concentration down to below the limit of quantification. If we do this early enough, we see this in regeneration 2, then we can also keep the concentrations below the limit of quantification for all the time, basically. And this has been working quite well for over 6 months now, but we will see during the course of the project how long we can really do this without exchanging any adsorbents. Here is another example I want to show you. It's the same groundwater for 9 months tested with a strong basic anion exchange resin. We cannot regenerate this resin, but I want to show you the potential here of these PFAS-specific resins. We see in blue the sum of PFAS, and in blue, the dotted line, the 100 nanograms per liter, which is the threshold value for drinking water for the sum of PFAS. And we see that we have been able to achieve a throughput of more than 40,000 bed volumes until we reach that threshold value. And just to give you an impression, this is up to 4 times as high as the bed volumes or throughputs we can achieve with the activated carbon that is used in the waterworks at the moment. And we can also the flow rate is twice as high of the activated carbon. So there is really some potential also in these resins as an alternative. But at the end, we have to see if it's also cost effective. And this is something we want to find out during ZeroPM. So potential applications, I was focusing a lot on drinking water here. That is probably the nature of working for a drinking water institute. But for the sake of completion here, we have also anion exchange applications in groundwater remediation and in treatment of industrial wastewater. And what we also want to test within ZeroPM is treatment of reverse osmosis concentrates. There are still some challenges and research gaps that remain. First and foremost, the limitation of capacity, especially for short-chain perfluoroalkyl acids. There has been good improvement in recent years. The manufacturers of resins have done great work here to increase the capacity of PFAS, but there is still work to do. And at the end, it needs to be a cost-effective solution. That is especially, again, true for applications in drinking water, because here very often the reason why we don't use anion exchangers is so besides the legislative regulations, maybe that the anion exchangers are better, but they are also vastly more expensive than traditional activated carbon solutions. So it has to be cost effective in the end. If you don't can use regeneration, then there's a need for safe disposal of the saturated resins. And here's the question: is incineration the most sustainable solution? If you find efficient regeneration, which from a sustainability point would be important, then you also need to find ways for destroying the PFAS in the regenerate and pair it with destructive technologies. And only then you will find the good sustainable solution. But this is what we strive for in ZeroPM. This is the message I want to put out here, that we try to find a very good sustainable solution for PFAS treatment using anion exchangers. So to conclude, the anion exchange is a PFAS removal method with great potential that can be used in various water treatment applications. And research and development in this area will continue to help improve the efficiency and the sustainability of this kind of technology. And with that, I welcome questions and thank you for your attention.
ZeroPM, Zero Pollution of Persistent and Mobile Substances. This project has received funding from the European Union's Horizon 2020 Research and Innovation Programme under Grant Agreement number 101036756.